Hello and welcome everyone to Clarios Pilot Dry Clean Room Project presentation. Here is a list of all your team members. I am Jared Rogers and I am a mechanical engineering student. Team members also include Caesar, Dakota, and Megan, who are also mechanical engineering students. We also have Dan, who is an electrical engineering student, and our faculty advisor, Dr. Sosen. Clarios, our project sponsor, manufactures lithium-ion batteries. This process needs to take place in a dry clean room. The current equipment requires manual intervention to maintain a dew point specification of negative 40 degrees Fahrenheit. This intervention is only needed during the summer months when the outdoor air is hot and humid. The Grand Valley State University team has been tasked with performing the analysis of the current dry air supply equipment and controls. From the analysis, we will make suggested improvements.
So the current system for dry air supply was examined, and the key pieces of equipment used to condition the air for the pilot dry clean room air supply are the makeup air unit MAU2, the main dehumidification unit DHU9, and the preheat dehumidification unit DHU12, which is used to supplement DHU9 during the summer months when it's hot and humid conditions. All of these key equipment are located above the pilot DCR in the mezzanine mechanical area. So this slide shows the current system with the main system components, MAU2, DHU12, DHU9, and the main rooms in the pilot dry clean room, which are the cell process room, PR4, the coat and dry room, PR2, and the mix room, PR3. The makeup air unit takes air from either outside the building or inside the building above the mezzanine mechanical area. The intake air can vary greatly in temperature and humidity depending on the seasons and if it is coming from inside or outside the building. The MAU2 conditions the air by either heating or cooling the air to a set temperature. When cooling begins, this begins the process of moisture removal. Once the air passes through the makeup air unit, the air can either go through the small dehumidification unit DHU12, or if dehumidification pre-treatment is not necessary, it can be mixed with the room return air and go directly to the main dehumidification unit DHU9. The air will then go into a plenum, which supplies the air to the pilot DCR through vent fans. This air is then vented out and recirculated back to be mixed with the intake air before DHU9. Also, from the schematic, you can see the locations of the sensors that are currently in the system, which include the temperature sensor, the humidity sensor, and the dew point sensors. So it is important to understand the function of the system components. A makeup air unit in a dehumidification system is designed to provide a building with tempered fresh air, both heated and cooled, to offset the air that is being removed through process exhaust fans inside of the conditioned space, which in this case would be the pilot dry clean room. So the MAU2 is the first unit the intake air goes through. It pulls in air from either inside or outside the building, or from both at 7,300 CFM, based on the schedule provided by Clarios. This air is then filtered to remove particles. The air is either heated or cooled to output a more desired temperature for processing. The MAU2 output air is then split by ductwork. About 4,140 CFM of the air is used in other parts of the building, while 3,160 CFM moves on to the dehumidification units.
The air then moves through DHU12, which is the smaller dehumidification unit designed to remove moisture from the process air. DHU12 is only used if pretreatment is required, such as in hot, humid summer months. If DHU12 is used, then 1,125 CFM of the remaining 3,160 CFM will travel through DHU12. In DHU12, a slow-moving desiccant wheel is heated by a separate stream of reactivation air, which heats and dries the top section of the wheel. The process air then moves slowly through the bottom section of the wheel, which absorbs moisture from the air. This decreases the absolute humidity and increases the temperature of the air. DHU12 has the capacity of outputting a leaving humidity ratio of 5.2 grains per pound in the processed air. This psychrometric chart shows the state of the air as it goes through DHU12. The air enters at a higher humidity ratio and lower temperature, then as it moves through DHU12, the humidity ratio decreases as the temperature increases. Regardless of if the air moves through DHU12 or not, all of the process air then moves through DHU9, which further removes moisture from the process air. This air is mixed with 5,840 CFM of return air from the pilot dry clean room. The process air then passes through a fan, various filters, and a rotating desiccant wheel in DHU9, which operates just as DHU12. Unlike DHU12, though, DHU9 has an integrated chilled water pre-cooling coil before the desiccant wheel. This allows the unit to remove more of the heat and moisture from the process air before entering the desiccant wheel. The humidity ratio leaving the unit after processing will be 0.073 grains per pound, which then enters the mixing plenum and the pilot dry clean room at 9,000 CFM. This psychrometric chart shows the state of air as it moves through DHU9. The process air is first adiabatically mixed with the dry return air. This mixed air then moves through the cooling coil, which decreases the air temperature but does not decrease the humidity ratio. Then the air moves through the DHU9 desiccant wheel, which lowers the humidity ratio and increases the temperature. In the mixing plenum, the air temperature is then adjusted for human comfort.
A baseline trend of MAU2, DHU12, and DHU9 were taken from the Metasys software system from January 24th to February 11th. A snapshot of the February 11th was plotted on the psychrometric chart, plotting the process from the outside air through the air handling system into the dry clean room. Outside air measured at 32 degrees Fahrenheit with a relative humidity of 61%. Output of MAU2 was 42.1 degrees Fahrenheit. The return air going into DHU9 at that time was measured at 58.2 degrees Fahrenheit at negative 45.4 degrees Fahrenheit dew point. The blended air temperature moving through DHU9 was measured at 45 degrees Fahrenheit. And the measured supply air going into the room out of DHU9 was 52.5 degrees Fahrenheit with a dew point temperature of negative 67.5 degrees Fahrenheit. MAU2, DHU12, and DHU9 make up the air intake system going into the dry clean rooms. There are also exhaust and relief fans coming out. The relief fans are controlled to cascade pressure from the center of the pilot dry clean room to the outskirts, creating a positive pressure flow out of the area. Each of the relief fans are controlled through the Metasys system. Monitoring of all air handling systems in the Meadowbrook facility are done using Johnson Controls Metasys software. There are temperature and dew point sensors located in various areas of the building, including outside, in ductwork from DHU12, in the return air and blend air duct of DHU9, the supply air leading from DHU9 into the dry clean rooms, and there are also temperature and humidity sensors located inside the dry clean rooms in pilot rooms 2, 3, and 4. Programming changes will be done by the company Andy Egan. The specifications of this project include maintaining a dew point temperature at or below negative 40 degrees Fahrenheit in the pilot dry clean rooms, to automate MAU2 inlet that controls the intake of outdoor and indoor air, to optimize the DHU12 trigger conditions, and to maintain a budget under $20,000.
We did not have any modifications due to the COVID-19 pandemic.
We have proposed 4 solutions to optimize the current dry clean room equipment. The first solution is to automate the MAU2 indoor and outdoor inlet damper. Currently, MAU2 does not take a mixture of outdoor and indoor air. It is either one or the other. We propose to automate this. MAU2 has the capacity to take in outdoor air on a hot, humid day. Per ASHRAE standards, it is required that we take in a minimum of 20% outdoor air. This will ensure that fresh air will be circulated throughout the room, but it won't be too much outdoor air that puts a strain on the equipment. Another proposed idea is to optimize the DHU12 trigger conditions. Currently, the equipment is turning on and off based on the room conditions and outdoor air temperature. This is a reactive measure. We want to be proactive to ensure the room never gets out of specification. We are going to have this unit be triggered by the air dew point temperature that leaves MAU2 and update the trigger condition for the dew point in the room. With the old trigger condition, our project sponsor was concerned with moisture moving into the dry clean room through the exhaust vents. We determined that even if the exhaust fans were not on, that the differential pressure in the room would provide a fast enough velocity through the vents that moisture could not travel upstream. This was then validated through an experiment of testing the airspeed in the vents. Isolation dampers will be installed into the vents to ensure we keep moisture out of the rooms in case of a power outage. The final proposed idea that we had was to seal all the leaks between the mezzanine and the plenum. There are many wireways that were not sealed properly. By properly sealing the mezzanine, it will reduce the chance of moisture entering into the mixing plenum and ultimately into the dry clean room.
For the implementation phase of the project, the Clarios maintenance team will install dew point temperature and temperature sensors near the return air damper. By using the sensors, the dampers will be automated with Metasys programming completed by a certified Metasys programming company. The dew point sensor within the pilot DCR will be triggered proactively at a dew point temperature that is above -50 degrees Fahrenheit. This will also be programmed into Metasys. Isolation dampers will be installed in the relief fan ductwork. This will reactively prevent the pressure and moisture from changing within the dry clean room. The GVSU and Clarios maintenance team will locate and seal leaks within the ceiling of the pilot DCR. The large gaps from electrical wire ducts will be sealed with a silicone latex caulk, which will reduce the amount of moisture that enters the room. The cost breakdown is shown in this table. All actionable items are shown on the left-hand side of the table. Some required items include sensors, dampers, programming, and caulk. Some optional items include the recommission of control volume boxes and addition of supply fan status to DHU9.
The improvements made throughout this project met the deliverables set at the beginning. First, and most importantly, the system can maintain a dew point below -40 degrees Fahrenheit throughout the whole year with no human involvement. The DHU12 will trigger on and off based on the dry clean room dew point and the dew point of the air leaving MAU2. MAU2 is automated so the inlet air supply can be switched throughout the year. Finally, the project cost was 50% less than the planned amount.
Some of the challenges the GVSU and Clarios team faced were delays due to COVID-19, an unexpected approval process with the Clarios leadership team, and complications in research and completion of calculations.